So, lab number three is really the first one that requires you to think consciously about testing your design, both in terms of the design of the test as well as the tooling and instrumentation required to do testing successfully. And so, I thought it'd be useful to talk about testing in VHDL in a little bit more depth than what we had done previously, and then talk about some of the implications of how you can do testing. And we start by noting that there's two fundamentally different approaches to testing your design. They can be complementary or they could be completely separate from each other. And it's a choice of what language or what tooling you're using to do the testing. And I separate between testing and test benches that use kind of the simulator infrastructure, or you call it simulator based, to design your test bench, versus language based. Another way to phrase that would just be, am I using model sim as my test bench? Or am I writing explicitly a test bench in my VHDL or whatever HDL I'm using here? There's no, one is right and the other one is wrong. And again, they can be complementary, but we can look at some of the advantages and disadvantages of either approach. So I have Model Sim already open here, and we can take a quick look at what the simulator-based approach looks like. And we know that because we have been doing this. So we have our lab number three design, and we would tell vSim to open it up, and as part of that test bench, we know that as we interface with the GUI for our design, there is an equivalent set of commands that it lets us know um, in that transcript window below. That for everything we're interfacing with the GUI, for the most part, it just shows what that equivalent command is below. So things like adding signals to our waveform, and now explicitly for testing functionality, forcing signals to have some certain characteristics. In this case, forcing this signal to be a clock. I'm not actually going to test this to be a great functional design, but just showing that as we force these values through the GUI, there is an equivalent command that's being shown down here that's corresponding to our test bench. So in this case, we're wanting to view a certain set of signals. That's all those sim, uh, add wave, the sim commands there. Um, and then there's explicit force commands that are saying, force a clock, and here's the syntax for doing so. And it's you want to look at that once and copy paste it and never have to remember that syntax, as well as for forcing some of the other signals in our design. And then there also could then be commands to actually run the design for a certain period of time before then potentially forcing the signals to be something else. In this case, we'll say run it for a little while. I didn't even set all the signals what they need to be. Perhaps then after having done so, I want to change this signal corresponding to the second input register to number 24, and then I want to run again a little bit longer. And that's showing what on the right hand side here, what's happening inside our simulation. I had mentioned this previously, but now showing it explicitly, you can take all of those commands that are in this transcript window and just copy paste them into a file. I didn't actually grab all of them here. That's the default run length. You would probably just want to specify amount of time, but we that's how we did it in the GUI, so that's how we'll copy paste it into the file. And we'd want to save that as just any sort of text file. Historically, those were referred to as do files, so I've stored this as testbench.do. And the reason you want to do this is because your design is not going to work the first time, right? I think you've all seen this. And the amount of things you have to set in order to successfully test your design is going to increase in complexity starting this week, and it's going to continue to increase in complexity. So you do want to at least start by doing this. You don't want to be spending time repeating over and over again the same number of sort of manual steps in order to get your simulation to a point where you can look and understand what's happening inside your design. So if I were to restart or to quit this sim and start it up again, um, as opposed to having to then go through the GUI and do all that stuff all over again, I can just type in the command as do, and any file name that has those equivalent commands in there will work. In this case, do testbench.do. It's going to run all those same commands, and we should have I didn't actually add the last few runs to the end of it, but that's fine. And it has the equivalent setup of what we had before. This is a very powerful thing. It's not showing all the power here in this example, but certainly it's very powerful in the sense that because it's being used using the simulator functionality, in this case model sim, it allows us, at least in theory, to do anything the simulator allows us to do. Anything that the scripting language that's underneath the simulator allows us to do. In this case, it's Tickle TK, which has a lot of advantages and is also kind of a, not very popular scripting language for people today. But there's Python-based simulators, there's Java-based simulators, there's really everything, and so it's extremely powerful. And you will look if you look online for more complicated designs, you will find examples that I'm testing a network interface that I'm building in Verilog or VHDL. I'm actually going to capture network packets coming off my network card in real life and connect those to the simulator using Python or Java or C code or any powerful programming language there. And your simulator allows you to do all those things. So it's extremely powerful. It's a definitely a large advantage in doing so. Um, some things are kind of hidden a little bit specifically in Model Sim. Um, I oftentimes would want to customize my waveform to be able to look for very specific things, right? For this example where I'm just simulating for 50 cycles and there isn't all that much going on, there isn't that much customization and there's not that many signals. But let's imagine, for instance, I have a whole ton of signals that I'm wanting to view at one time. All the items in this design, and this is your lab number 3 design, is going to have this many signals. It's going to go on and on and on and on and on forever, and there's just so many signals. And you're going to want to have most certainly some mechanism to visually process all this information. And ModelSim lets you do that. Let's say these first 3 signals are the most important ones to me. Um, I should be able to add to that signal a new divider. That's just a visual divider. Call it, I don't know, my divider. I mean, call it whatever you want. Signals for this component that I'm only wanting to look at right now. And that's just a physical divider that just segments that. Or specifically, I have so many signals I'm wanting to look at, and every time I restart simulation, it takes me a long time to keep track of what is what. Let me make sure that those signals I'm most interested in are a beautiful medium violet red. Now, I gotta be a little bit careful with choosing red here because red is also bad, right? Red is also undriven signals, and I have some signals that haven't been driven properly here. Green we're already using. Let's do this kind of aquamarine. Okay, just a different set of colors. So in order for us to distinguish different signals in our design and different functionalities here, and for whatever reason, when you make those changes in terms of the visual feedback of your waveforms, ModelSim isn't actually adding it to the transcript window here, but they do provide a separate piece of functionality to store and save that information, and that's so-called save format. So Control S or just save format, and it'll specify a do file where you can actually save it in, and we can open up that file, and it's going to give us the syntax for scripting that. Let's open that in a good text editor. Okay. That has all the things that actually added all the waves, so we wouldn't want to run both of these. This is viewing all the waves in our design. There's syntax that makes it a little bit cleaner, and then there's the actual syntax for configuring dividers and changing the color of certain signals we have in our design here. That's very useful in terms of your design's going to have hundreds and thousands of signals in it. You're going to want to simulate and look for something very specific. Between time 1 second and 1.1 second, I'm only looking really of these millions of signals. I'm only looking at these 7 signals. Set your waveform, save the format. Every time you rerun your simulation, you're not only potentially forcing the values that are most relevant for you, you're also having the view look exactly the way you want it for things to work. So certainly, this is very powerful. In terms of any downsides or negatives of a simulator-based approach, and arguably the reason we don't use it as our primary approach, and it's only a complementary approach, is it adds that software dependency to your project. If you build your test bench entirely in ModelSim, you've now created a project that only works in ModelSim, right? And that's a dependency that's either just expensive or complicated or very large, and that dependency then requires that if someone wants to test the design with the test benches you've created, they have to use ModelSim. Potentially, they have to use that very exact version of ModelSim because things do change over time. So we compare that approach to the language-based approach. Again, we're still using ModelSim, so the the simulation-based approach is still there. We're still using ModelSim to simulate things, but now we're using our VHDL syntax to actually do those things for us. And we've done a little bit of that. It's going to get a lot more complicated now, starting in lab number 3, where we have some component we're looking to test. And this module will be provided for you. It has a series of inputs. In this case, it has a clock, and it's going to take a few cycles to simulate what we want to simulate. We do a structural port mapping of the individual entity we're interested in testing via either some top level signals or some internal signals that we're mapping inside our test bench. Right, this isn't corresponding to any physical hardware anymore. Right, if we were to draw logically what's happening here in the language based approach, we would be having our testbench.vhd, and inside that there's structural code, our so-called design under test, that we're then port mapping, and generally it's inputs and outputs, right? We're forcing input values, and we are reading back output values, and we're interested in seeing the result of those values, as well as then followed by some sort of behavioral logic, which we don't necessarily draw as corresponding to hardware anymore because it doesn't have to correspond to hardware anymore. In your VHDL test benches, you can read signals from files. Um, you can do all sorts of things that have software-like functionality. But the point of that behavioral logic isn't to describe any hardware any longer. It is to force values, potentially read the results of values. We've done a little bit of that in lab number 2, but you're going to do a whole lot more of that starting in lab number 3. And that's why we do see all this behavioral VHDL with one or potentially multiple processes to do things that we otherwise would have been doing in ModelSim via those force commands. This process, which is setting the clock, is the equivalent of that force command for the clock. We would specify somewhere as a constant, in this case, what half a clock period is. So for a 10 nanosecond clock, that would be set as 5 nanoseconds. And literally, that would be set as a constant of a type time, where in our behavioral code, and we can talk a little bit about, in the interest of time, we won't talk too much about it, of how that sequential statements that are from top to bottom, where we're going to set a value to 0, we're going to tell the simulator to not do anything for that half a clock period. We're going to set clock to 1, and then we're going to wait. Now, the reason this works is because the way processes work in VHDL, that we start at the very beginning, and sequentially we go line by line. And when we get to the end of that process, unless there's a statement telling us explicitly to stop forever, just the word wait would allow us to do that, we go back to the very beginning. And we can visualize that as our process block. And we'll insert some potential sensitivity list there, and a series of statements. And our execution flows sequentially. Again, unlike our data flow, in which everything is concurrent, everything is happening at the same time. The order of things do not matter. Here, your orders do matter. We go all the way through line by line, and then we work our way back to the top. So you can already sort of see maybe the main disadvantage of the language approach. To put it succinctly, it's VHDL. Right? It's got the disadvantage. It's VHDL is tough, and it's got lots of things you can screw up and can be very hard to debug. And that is also the case for the test benches that you're creating in VHDL. The main advantage, though, would be portability. Then, sort of the corollary. So VHDL is a disadvantage due to just the complexity of the language as well as the features of the language. There's so many more things you can do in a software simulation-based test bench than you can do in your VHDL-based test bench. But for this reason of portability, we tend to at least have some hybrid approach where the VHDL is doing some of the mapping of our design under test, and then we still use the simulator when we want our signals to look a certain way or to view them in a nice visual manner. So it's always a combination generally, but that's the main disadvantage. And that's what your VHDL test bench is generally going to look like. So we have as many processes as we think we need to set the various signals in the design. We could do this within one process as opposed to multiple, but it doesn't matter. And again, we're no longer describing hardware in these processes. Right now, we're just setting signals. Literally, we have a flip flop. Let's set the reset signal to 1, the write enable to 0, as well as the input data line to 0, and let's wait for a whole clock cycle. It's going to do that sequentially, and then it's going to wait for that 10 nanoseconds, 100 nanoseconds, whatever it's set as. You can think of each of these blocks as effectively being our test inputs that we're driving into our module that we are testing. You could have built the same exact functionality using the tickle commands in our transcript window for our model sim. There's just the disadvantage of portability of that type of approach, where now you need model sim to simulate your design. This test bench will work in any type of simulator that we have there. So we can definitely see that this behavioral VHDL is potentially more powerful. One final thing I want to leave you with in terms of a big gotcha that you may not see um, in Lab 3, but will be coming later this semester, is this issue of using behavioral VHDL in your design to actually model hardware. In this case, where it's just our test signal generator, there's no harm. It's not describing hardware. We're never going to synthesize that file. It's never going to correspond to hardware. But for things that we're looking to model actual hardware using behavioral VHDL because of its powerful abilities and the extra syntax it provides, we're going to have a process block that may, for example, look something like this. And I'll describe what's happening here relatively briefly. Where we have a process, we have a so-called sensitivity list. The list of signals that this process is sensitive to that will trigger this process's execution. And we have something going on in there. In this case, C equals A and B, and then N process. This is a perfectly valid way of describing an AND gate in hardware. It's behavioral VHDL and it's sequential statements as opposed to our data flow VHDL. It is a perfectly valid way of doing an AND gate. Maybe it's not the most efficient. We know we can do an AND gate in one line of data flow. It's a built-in operator. We don't generally need to be making AND gates as separate, top-level components in our design, but it's perfectly valid. It is describing a circuit in which there are inputs that are sensitive to it changing, and it's calculating an additional signal based on some functionality. Here, unlike in the example for our test bench where we were seeing that syntax that looked like wait for, we would not have and could not have any such wait tight statements in here. Another way to think about it is, for this example for our test bench, it makes sense to tell the simulator, wait for 10 nanoseconds, and then set some more signals. In terms of describing hardware, it's not at all clear what it means to wait. What does it mean to describe a piece of hardware that waits? Okay, we can think about it. You have a clock and you have a counter and you're checking values, but it's just not something that's synthesizable. So these processes tend to look a lot different. These will have in your test bench your wait statements and probably no sensitivity list because it doesn't need to be describing hardware. These, the behavioral VHDL that's attempting to describe hardware, will always have sensitivity lists and it will never have wait statements because it doesn't mean anything to describe hardware that waits. We're describing still arithmetic and logic flowing through a circuit with wires and not something that is just software that's waiting for a certain period of time. So this circuit does definitely describe as in as valid of a manner as the data flow equivalent an AND gate with A, B, and C described here. Where things start to get a little bit messy and where you have what I would describe as, hour-long, multi-hour-long bugs are when you have what's referred to as an incomplete sensitivity list. Let us just say, for instance, that I designed this module and I did not have B in my sensitivity list. ModelSim won't warn you. It is simulating what you're asking it to. Well, let's think about that. What does it mean to have this C set as A and B for an input that's not sensitive to any changes in B? It implies, and the functionality ModelSim would show this, that when you get an A transition from 1 to 0, C would certainly change immediately afterwards or after some delta delay. But if B changes, it would not necessarily affect the output of that C circuit. So in fact, if we have our A here, what this circuit is describing is an equally valid circuit. It's just probably not the one that you wanted. It is describing a circuit in which A is an input to that gate that we're inferring there, but B is actually connecting to a latch. And presumably you don't want that to be the case, right? It's A where the output C changes whenever A changes, but when B changes, we're just latching that we latch that value. And in fact, what we're actually computing is whatever old value of B is ANDed with A. And storing, we're inferring some storage element, some latch in our design for this to work properly. ModelSim will give you exactly that. And it will give you no warnings because it is doing what you're asking it to do. What will then happen? Of course, presumably, if you have that happening in your design, you're going to see that as, my AND gate's not working properly. It can be subtle though. What if 99% of the time, every time a B changes, A also changes? Well, then you may not catch it except for that 1% of the time. That can be a pretty brutal, just behavioral simulation bug you have to track down. The other big gotcha when you design behavioral VHDL with incomplete sensitivity lists is the so-called simulation synthesis mismatch. And we talk about errors in our designs, and I'm wanting to minimize, hour-long errors and turning them into minute-long bugs that you're having to deal with. The simulation synthesis mismatch errors can be days and weeks, and that can be extremely painful. What will typically happen is even if you've specified an incomplete sensitivity list in your VHDL, and ModelSim is very happy to consume that and give you exactly what you've inferred, your synthesis tools won't. And you'll get a tiny little message that says, incomplete sensitivity list detected, inserted B into the sensitivity list. You might say, well, that's what we wanted. We wanted an AND gate, and now we have an AND gate. The problem is your test bench is now telling you one thing, and your actual inferred physical hardware is doing something different. And that's a very hard thing to track down. And so, in general, we want complete sensitivity lists. VHDL now allows you just to specify without worrying about the names of your signal, just process all. Every possible signal that could be in my sensitivity list, put it in there. Maybe it simulates 10% slower, I don't even know, but it's certainly going to save you from those sort of issues. So, again, big picture takeaway for lab number 3 is we have to be very careful about the design of our test bench for this. We could talk separately about, how you're actually going to determine what signals you're needing to set for your test bench. You're basically manually creating the control logic yourself for week 3, as well as for lab number 4 coming up in the following week. But using our VHDL, there's this powerful behavioral syntax we can use. We just can't use that to infer hardware. And when we later use behavioral VHDL to infer hardware and to describe hardware, we'd be very careful with things such as our sensitivity list. Otherwise, let me know if you have any questions. Looking forward to seeing everyone's lab number 3s. Thanks.